Okay, my name is Clemens Kolbic, and together with my colleague Sylvester Kyle, we're going to talk about fuzzing and exploiting wireless device drivers. Just a short outline for today. The first thing we're going to talk about real briefly is 802.11 fundamentals, so how does wireless protocols work. The second thing we're going to talk about is the fuzzing of the wireless protocol itself. There are several issues connected to that, and we're going to talk about how we might overcome these, and that's the third point, actually what we call virtual 802.11 fuzzing. That's our new approach to do the fuzzing itself, and we're also going to have two short demonstration of our new tool. And as a fourth part, as the last part, Sylvester is going to talk about how we could maybe exploit the things we find with fuzzing in kernel mode. Okay, to give a short introduction, of course, first about ourselves. Right now we're two students at the Technical University here in Vienna. We ought to be working on our master's theses, like Engin probably knows, but we have quite a lot else to do. One thing we did is the work that we present here. This is the result of a vulnerability seminar that we did at our Secure System Lab together with SecConsult. For those of you who don't know SecConsult, it's one of the only companies in Austria that do high-tech research in the security area, and they have regular participants at conferences like Black Hat or DeepSec right now. And what might be interesting for you guys is that they have a vulnerability bonus program where they buy new vulnerabilities. So there's one way for you guys out there to make a little money, and there's a URL and also an email address on there, and it will be on the wiki so you can look it up later if you're interested. So to get back to our real wireless playground, first, all of us know that wireless networks have become a wide standard. Like every one of us has probably some wireless device, either in your laptop, in your standard computer. You also already have them in your phones, you have them on your PDAs, even on your MP3 or video players. That basically means that there's a vastly increasing number of potential targets out there. And what's even better about it is that the communicating software, the device drivers, operate on a very low level supervisor mode, that is kernel mode in Linux talk. So every vulnerability that we find in there turns out to be extremely dangerous and a lot of fun to play with. So we're going to give you a short 802.11 primer. For those of you who know the protocol itself, I know this is really a summary of what's there, but that's all our time gives us. So to see where we're operating, most of you probably know this picture. It's the IEEE 802 family for connecting computers. And we have a lot of standards in there, but the one that we're interested in is on the right, on the blue. That's the 802.11, which is wireless communication, and it's split up into two layers. The first one is the physical layer on the bottom, which is divided into multiple sections where the device treats things like different transmission modes and so on. Everyone has heard of A, B, G, and so on. However, we're not going to deal with that stuff because that's all melted into your hardware, so we don't want to exploit your hardware. I mean, you can go ahead, but we don't want to. What we deal with is the thing above. It's the MAC layer, because that's in software and we can deal with that stuff. Okay, so inside the MAC and inside the wireless protocol altogether, we have three different types of frames. We have management, control, and data frames. The management frames are there for really advertising and connecting to networks, wireless networks. The second thing, control frames are really used for management of who is talking when and so on. However, we don't really go into the control frames because we don't see any potential vulnerabilities in there. And the third type is the so-called data frames, and that's exactly what the name suggests. It's really for transporting higher level protocols over the wireless medium. Down here we have a picture of a management frame, and it's made up just like any protocol usually. So we have a header, we have a frame checksum at the end, and we have a body. We have multiple addresses, I will get to that in just a second, and inside the body we have so-called information elements that carry information about wireless networks, and I will deal with that in a second as well. So here we have what is called the wireless states. We have three different states, which basically divides the types of packets that might be sent over a network. We have state 1 where both devices don't really know anything about it or about each other. We have state 2 where they have little knowledge about each other, and then in state 3 we have full knowledge of both devices and they can transmit higher level protocols. And how all that works can be seen in what's so-called association of two devices. In this example, we have an access point on the left and a station on the right. And I will just show you how this works out, how they can connect to each other. The first thing we have on the left side, on the access point side, we have that the access point is sending out so-called beacon frames. A beacon frame is nothing else than a management frame that contains information like, hello, there's a network available, its SSID, its network name is, I don't know, my network. I'm talking on channel 9 and I support the following rates. So that's all there is about this beacon frame. The second thing that is there is the station's first thing it can do to get a connection is send out a probe request. It's again a management frame of a special type, and it just says, hi, well, I want to know more about your network. So when the access point gets a probe request, it will reply with a probe response, and again, including the data that was in the beacon frame, and it might add some additional information. But basically, a probe response is nothing else than a beacon frame, but sent out as a reply to a request. So when the station, for instance, my laptop says, hey, I want to connect to that device or to this network, it sends out an authentication frame. The authentication frame is basically, hi, well, my MAC address is something, and here's sequence number 1. And if the access point wants to build up a connection with that station, it just sends back, yeah, hi, there's this my authentication, there's sequence number 2, and this is my MAC address. Although authentication might sound something like security, it really has nothing to do with it. It's really just exchanging MAC addresses and sequence numbers so they have a starting point to build their connection on. So as soon as this authentication has been done, we're in what we saw before called state 2. This is authenticated but not associated. So the next thing that has to take place is the association itself. Again, it's a request from the station basically saying, well, I know your MAC address, hello, Mr. Access Point, I want to connect to your network. Here's the parameters you might know need for authentication. And if the access point wants to build up the connection, it again replies with an association response welcoming this new station in the network. Right now, after this association, we're in what we saw before, state 3, where we can send higher level protocols that might be UDP, IP, UDP, IP, TCP, IP, and so on. And they might also start doing some encryption, send out key information files, and so on to get real encryption and authentication in the network. So we now know how wireless communication really takes place, and I'm going to talk a little bit about fuzzing and what's the problem with fuzzing wireless protocols. Well, the first thing is that typically fuzzers go ahead, I mean, I think you all know what fuzzing is really sending out tons of probably random data and see just what happens. But there's a huge problem when doing this with wireless devices. There's been some or even a lot of talk at the Black Hat Europe this year about fuzzing wireless device drivers. But they really stated some issues they simply couldn't deal with. One thing was the frequency channel problem. Whenever a laptop sends out a frame, for instance, probe requests, saying, well, are there any networks in the area? It sends out this frame at a particular frequency. And if it doesn't receive anything in a few microseconds, it will change the hardware frequency to some other frequency and then send the packet again. So whenever you send out some fuzz data at frequency channel 1 and laptop is in frequency number 3 because it's constantly iterating through all frequencies, you're just missing tons and tons of data and you don't even know it. So that's a really big problem. Another thing that we have is that there's a lot of hardware filtering going on with the incoming packets concerning the BSSID, the network ID, and also of the states that you saw before, state 1, state 2, state 3, because when we're in state 2, and the hardware knows that, it won't even accept state 3 packets. So we might send out pretty cool fuzz data frames, but it just gets dropped right away at the hardware, and we have no idea if the thing we send out really hits the actual software. The second thing we have that's a little bit connected to the frequency hopping that I was talking about before is response and timing constraints. Because there's a lot of traffic going on when we talk about a wireless network. We have the problem that whenever a laptop or some device sends out a request, the incoming reply has to be really quickly. So there are timestamps in each single frame, and as soon as a incoming packet comes in too late, the hardware just drops it. So again, we have the problem, did the fast packet really go up into the software, or was it dropped in the hardware? And so that's another big problem we have. And there has been attempts to really parse incoming data with a laptop in monitor mode, really look at the packet and inject reply packets, and that's just too slow, it just doesn't work. Another thing we have with wireless communication is the problem of overloads, interference, packet corruption, and so on. We have a frame checksum in management frames. As soon as there are two packets at the same time in the air, the hardware will drop the packets right away because the frame checksum is just wrong. We might have multiple wireless networks in the air. I mean, how many networks are available at your home? You know, there's probably 3 or 4. Everyone uses some unencrypted, right? So we have a big problem with packet corruption, and that's another thing. And the last thing we have on the slide there is not really an issue of wireless fuzzing, but of fuzzing altogether. We have the problem that we're really bombarding a target with packets, but we never really know when it crashes what was the last packet that really made it into the driver or into the software that we're attacking. So monitoring a target is really always a hard thing to do, especially if you don't know which packet made it into the software and which didn't. And as last thing, we have a kernel mode fuzzing right here. So how do you debug kernel mode things on a remote target and make it easy, make it fast, and so on. So we have a lot of issues that we have to deal with. So another thing we have to ask ourselves is, what do we want to fuzz? We saw before that we were mainly dealing with management frames, and that the body is made of the so-called information elements that hold the actual data inside a management frame. Those information elements are made up of the type length value pattern. And you can see it down here, maybe some of you know, but basically it's just the first byte or the first couple of bytes, fixed length, saying what is this information. The second couple of bytes say the length, and then there's the length bytes of value, and your security researchers, you know where the problem with all that is. You have a length field, you have data, yeah, there's gonna be some overruns and things like that. So we know, yeah, overflowing is potential, so we really take a close look at that. So here we have the example beacon frame I was talking about before. Here we see we have the header on the left top, we have a frame control, which basically says this is a management frame, it's of type beacon, and so on. We have an ID, because we need that in protocols. We have 3 addresses. One is the source, where is it coming from? One is the destination, where is it going to? And the BSSID is usually the MAC address of the router that is responsible for sending on packets, because 2 laptops might not reach each other, so they send it to the router and it will just forward it to the next router. We have the frame checksum at the end, and here we see the body. We have a timestamp that I was talking about before. That's why we have the timing difficulties and some additional information. And then we have 3 information elements. The one at the top is the SSID, which says, well, it's ID 0, it has 9 bytes, and it's just characters, just saying my network. The second one is the supported rates. So in the beacon frame, the access point saying I can talk to you on rates 11, 14, 21, and so on to 54 or maybe 100 and whatever is possible nowadays. And the last one is just ID. I think it should be, say, ID2, which says, well, I'm currently communicating in frequency 9, because you could receive a higher frequency, because you can never send it exactly at one frequency, so you know exactly where this communication is taking place. Okay, so we heard about wireless communication, we heard about the protocols, and we had heard about the problems we have when fuzzing with it. So we came up with what we call the virtual 802.11 fuzzing. And for our new approach, we took the requirements I stated before, just to sum them up once more and try to overcome these. So the first one we tried to eliminate were the timing constraints. We don't want to have to be fast to reply to a packet. This is one major requirement. The second one is this unstable virus in the medium. We don't want to send out packets and being